Hi students, welcome to Mrs. Lee's Chemistry Academy. Today we're going to cover Module 6 on atomic structure and periodicity. Basically on electromagnetic radiation, hydrogen spectrum, and the Bohr model. Now why do we need to study this? Because if we know the inner structure of an atom, then we can relate it to the trends in the periodic table, and then we can understand chemical bonding, and then that will be leading to chemical reactions. Tying to the learning objective from College Board 1.13, the student can justify the selection of a particular type of spectroscopy to measure properties associated with vibrational or electronic motions of molecules. First, we need to understand the wave nature of light. Light is an electromagnetic radiation that travels as waves. So when we talk about wave, we talk about wavelength, which is the distance between two peaks or two troughs, and measured in the unit of nanometer. Now nanometer is 10 to the negative 9 meters, so that's very, very short. Frequency is the number of waves that would go by per second, and it is in the unit of second minus 1 or hertz. Wavelength and frequency are related through a constant called the speed of light, which is 3 times 10 to the power 8 meters per second. Wavelength and frequency are inversely proportional to one another. That means as the wave gets longer, the frequency is lower, or when the wave is shorter, then the frequency is higher. Now when we look at the electromagnetic spectrum, there are several parts to it. Starting with the left-hand side, we have the high energy, high frequency gamma ray, followed by X-ray, followed by ultraviolet, followed by the visible region, which is the colors that we see, followed by infrared, followed by microwave and radio waves. Now on the gamma ray side, you will notice there are short wavelength, high frequency, high energy. On the other side of radio waves, you will notice long wavelength and low frequency. In the visible region, we go through Roy G. Biff, red, orange, yellow, green, blue, indigo, violet, with the red color light being longer in wavelength than the violet light. In the electromagnetic spectrum, the gamma ray is actually produced by the sun or stars or any unstable atomic nuclei. The X-rays are what we use in medical imaging of bones and internal organs, and if we have too much exposure, it could be damaging our biological molecules. Ultraviolet radiation comes from the sun. Excessive exposure will cause skin cancer, cataract, and skin wrinkles. Visible light is the rainbow color. Infrared is emitted by warm objects and often used in night vision technology. Microwaves are used at home in a microwave oven or in radar. And radio waves, they transmit signal responsible for AM and FM radios, your cell phone, and television. Dual nature of light. Max Planck, he discovered that energy can be gained or lost in whole number multiples of a quantity called h nu, or small packets called quantum. Imagine you are having a staircase, you'll be on each step, but you cannot be in the middle of a step, and that's what h nu means, a whole quantum. Now, energy is equal to h nu. H is a Planck's constant. So when light strikes a metal surface, the electrons are emitted. This is known as photoelectric effect. And Einstein, he analyzed the kinetic energy and number of emitted electrons, leading him to propose that electromagnetic radiation travels in a stream of particles called photons, each with energy h nu. And therefore the dual nature of light, that light is actually particles and it travels as waves. Now, the energy of photon can be calculated as h nu, or h times the speed of light over wavelength. Practice problem number 1. Arrange the 4 types of electromagnetic radiation: gamma, radio, blue, and red light in the order of wavelength, frequency, and energy per photon. Now, in terms of the wavelength, this is the ordering. Gamma ray would be shortest in wavelength, while the radio wave will be longest in wavelength. In terms of frequency, it would be just the reversed order because frequency and wavelength are inversely proportional to one another. So the lower frequency will be the radio wave and the high frequency will be the gamma rays. And so is energy, also directly related to frequency, therefore in the same order of arrangement. Practice problem number 2. The red light has a wavelength of 633 nanometer. Calculate the frequency and energy of a photon and 1 mole of photon of red light. Now, taking the wavelength of 633 nanometer, first we convert it into meters. And then we plug it into the equation, having speed of light divided by the wavelength. We end up with a frequency of 4.74 times 10 to the power 14 second minus 1. Now we calculate energy is h nu, which is Planck's constant times frequency. By the way, nu is the name for the frequency. So it is 3.14 times 10 to the negative 19 joules per photon. Now, if you want 1 more photon, we multiply that by Avogadro's number, and turns out to be 1.89 times 10 to the power 2 kilojoule per mole. Niels Bohr, he pictured an atom as having the nucleus in the center, and surrounding it are these energy levels, and the electron would orbit around the nucleus at different energy levels. And he also pictured that excited electron, they can jump from a lower to a higher energy level when they absorb energy, but the excited state is unstable. So the electron soon fall back to the low energy state, and it gives off this energy absorbed in the form of electromagnetic radiation. Now, if that radiation has a frequency or wavelength matching that in the visible region, we can see colored light in the emission spectrum. If we look at the white light with a diffraction grating, you'll see the rainbow color Roy G. Biff. However, if we put a tube of hydrogen gas molecules and connect it to some power source and we excite it with electricity, the electron of the hydrogen atom will then go to the high energy level and then falls back down to a low energy level and give out these colored lines, which are violet, blue, green, and red at the characteristic wavelengths. Therefore, we see the 4 lines in the hydrogen emission spectrum. And they can be used as fingerprints to identify the element. So here's a diagram. On the right-hand side, you see the nucleus in the middle, and around it are energy levels orbiting around it. And you see the electron going down from a higher to low energy level, and give off the color lines as red, green, and blue. And on the left-hand side, you can see that as another representation of how electron would transmit between energy levels. Please note that the energy levels are not equally spaced out. That means the difference in energies are different. Remember in the lab that you may enjoy doing a flame test. This is putting a nichrome wire into an aqueous solution that contains the metal ion of interest, and then you heat it up in the flame. And then it will then give off some specific colors. That's a combination of several spectral lines in the emission spectrum. And some of the colors that you may have dealt with would be red for lithium, and yellow flame color for sodium, violet for potassium, orange for calcium, red for strontium, yellow-green for barium, and green-blue for copper. They're really beautiful colors. Now, Niels Bohr, he calculated the energy of an electron, and he used the following formula. Energy at a particular level is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n squared, where n represents the energy level. Now, why do we have a negative sign in front of the formula? It is because when you imagine this electron is infinitely away from the nucleus and with no attraction whatsoever, we call that a ground zero, energy zero. But as the electron gets closer and closer to the nucleus, now we're going from ground zero down to the basement, and therefore we have a negative sign in front of the formula. Here's a problem calculating the energy emitted if the electron goes from energy level 5 to energy level 2. So we plug it into the equation, noting that the energy level 5 square will be 25, and for energy level 2 square will be 4. So we calculate the energy between energy level 2 and energy level 5. And we calculate it to be negative 4.58 times 10 to the negative 19 joules. Now, de Broglie, he came up with the definition of a wavelength associated with a particle, and he said wavelength is equal to Planck's constant over the mass of the particle and the velocity of the particle. So here's a problem. Knowing that the electron has a mass of 9.11 times 10 to the negative 31 kilogram, moving at a speed of 3.58 times 10 to the power 6 meter per second. Calculate the wavelength, plug it into the formula, we have 2.03 times 10 to the negative 10 meters. Infrared spectrum. Now, the infrared radiation, they can excite the bond of a polar molecule to make them vibrate, producing a change in the dipole of the molecule. Now, if we imagine water can be excited and causing the bond to stretch either symmetrically or asymmetrically or bending by infrared radiations. And the different kind of molecular motion can then lead to absorption or emission of photons in different regions. Here is the spectrum showing that of ethanol C2H5OH. Now in the infrared spectrum, we have on the y-axis the transmittance in percentage, and on the x-axis we have wave number. Wave number is the inverse of wavelength in the unit of centimeter minus 1. If you look at this spectrum carefully, you know that there's a broad band at about 3,400 centimeter minus 1, that's for the OH band. And then there's another absorption near 3,000, that's for the CH bond. And then there's another one at about 1,400, a broader, flatter absorption band, that's due to the single CC bond. And then the CO bond happens at about 1,100 centimeter minus 1. So that can be used as like fingerprint for identification of the bonds in a molecule. With the UV visible spectrum, it has to deal with the transition of electrons between energy levels. It can be used to probe the inner structure of molecules such as metal ions or organic compounds. Now, it is a light passing through a colored sample because remember, there are d orbitals and there are 5 of them. 3 of them are slightly lower in energy than the other 2. So when this electron, they can move from a lower to high energy level by the excitement of light, and that will produce a spectrum. So in here, we have the spectrum of beta carotene, which has absorption on the y-axis and the wavelength on the x-axis. And you see there's a maximum absorption at 460 nanometer, which corresponds to that of the blue-violet region. Now, if you look at that pie chart, if the blue-violet light is absorbed, that means the color of orange will be transmitted, and you can see orange color for the beta-carotene. One very useful function is to use Beer's law to calculate or estimate the concentration of an unknown colored solution. Now, Beer's law states that absorbance is equal to EBC, where E represents the molar absorptivity of that substance, and B is the path length that light travels through, usually 1 centimeter, and C is the concentration in molarity. Now let's talk about Beer's law, which is most useful in determining the concentration of a colored solution. Here we're using absorbance, which is related to EBC. Now, E refers to the molar absorptivity of a particular solution. And B is the path length in which the light travels through, which is usually 1 centimeter. And the C representing concentration in molarity. So we would then use the colorimeter. We would set it at a specific wavelength where the maximum absorbance will occur. And then we will prepare the solution, and then we will run it in the colorimeter to generate some data of absorbance versus concentration. And then we can make use of the data to draw a line of best fit, a straight line, from which we can determine the concentration of an unknown solution. So here's practice problem number 4. A student, he wants to determine the concentration of nickel sulfate, a green solution, based on absorption of light. And he's given a standard solution of 0.4 molar. 1, design an experiment to collect data. 2, determine the concentration of the unknown solution. And 3, talk about a possible source of error. So to prepare the standard solution, we call that serial dilution. That means you start out with one solution and you gradually dilute it down to a number of other solutions. And then we run it in to generate a standard curve. At this time, you'll be using M1V1 is equal to M2V2 calculations. So if you, let's say you want to make 10 milliliter of 0.32 molar solution from a 0.4, then you would have 0.4 molar times V1 equal to 0.32 molar times 10 mil. And then you calculate your V1, and that's the amount you will pipette out of the 0.4 molar to dilute it down to 0.32. Now here we're setting the calorimeter at 635 nanometer, where the maximum absorbance will be obtained. And after we prepare the serial dilution, then we will put one at a time into a cuvette, a small little plastic long thing like this. And then you put it into the calorimeter, and we can run it to record the absorbance. Then we plot the absorbance versus concentration, and then we then run the absorbance of the unknown and fit it into the strict line of best fit. So here are the data of a concentration of the standard and the unknown versus absorbance collect. And the student obtained the following chart, and he graphed it. Then, from the line of best fit, he determined the unknown concentration by knowing the absorbance, which is about 0.462, and he came up with a 0.31 molar for the concentration. Now, then the error could be this. If the student forgot to wipe the cuvette clean of his fingerprint with the Kim white tissue, then there will be fingerprint left on the cuvette, and that will block some light and absorb more light, and that would then yield to a higher concentration. So to sum up what we have learned today, 1, we learned that electromagnetic radiations are characterized by wavelength, frequency, and energy. 2, we understand that there's a dual nature in radiation. They act as a quanta of photons with wave-like properties. And we also examined the emission spectrum of the hydrogen accounted by the Bohr model. And we also looked at various flame test colors. And we also calculate the energy that's given off when electron goes from one energy level to another energy level. We also applied de Broglie's equation to calculate wavelength. And we examined the infrared and ultraviolet visible spectra on how they can provide information on the bonds and the electronic structure of an atom. And then lastly, we applied Beer's law to determine concentration of an unknown solution, which is same as the idea as your investigation number 2 in your lab manual. So I hope the above information has been useful to you. From the team of MLCA, we want to thank you for watching and hope to see you again next time.